Okay, well, today we're going to be kind of going over kind of the scientific background behind geography, because we have to understand geography is an applied science. It's about how we use the earth, how we map the earth, how we chart the earth, how we use it, how we're distributed around the world. But while all the major academic disciplines have a lot of principles in common, like I said, they're a little different from each other. With history, it's all names and dates, but also dig deeper, motivations, ideas, human nature. Political science very similar, but not as much concentration on names and dates. But with geography, it's how we use the world, how the world works, both in physical terms, in terms of use of natural law, but also how people use it. So look at a lot of different scientific concepts and a lot of different demographic concepts. And so we begin with one of the most basic and established principles in science, which is how do you find things out? And that is the scientific method. Famed and song and story. Scientific method is a process of inquiry, of experimentation, and discovery. But there's several basic steps behind it. The acronym we always used when I was in college was David's can't find the dead cat. That's the thing with acronyms, bad memory. They're designed to get your attention. First, define the problem. It doesn't necessarily have to be a problem, but just what are you trying to figure out? Second, collect research. Like I say, research, the most important part of it. Figure out what's been written on it before, what we know about it. What do we know about this problem? What kind of data do we have? And data and information, that's the most important thing you got in science. Look at the numbers. What are the numbers telling you? The F part, formulate a hypothesis. This is a guess. Why are you seeing what you're seeing? Um, um, got all your research, your data. Got this problem here. Why is it working the way you expected to? Why is it working a particular way here? Or projecting on this data forward, what do you think is going to happen? Given all these basic set of scientific principles, all this data you have, what's going to happen moving forward? Then you test your hypothesis. This is your lab experiment portion. It can be done in a traditional lab with beakers and test tubes and everything, or it can be out in the field and the world, just observing what you see in nature. Like I said, this is very common with um, geography and astronomy, geology. You go out and you see what's actually there. Then you test your hypothesis, see what the results are. Now, the testing part, it can go on numerous times. You test it, retest it over and over and over again. It could be dozens of times, hundreds of times even. In fact, in biochemical research, and medical research, these hypotheses are tested hundreds of times. Especially if you're experimenting with a new medication, you want to make sure it works, so you have to have hundreds of tests. Then you look at the data from these tests. What happens in each case? And from there, draw your conclusions. Draw your conclusion. What happened in these tests? What happened in these experiments? Did you have any anomalies? Did it meet your expectations, what the initial data says? If not, why not? If so, why so? And from there, communicate results. Communicate your results. That is, tell the world what you found out. And that's when you publish in the professional journals. What you usually do is you publish in what they call a peer-reviewed journal. That is, when you send it off to the magazine or journal, whatever to be published, they have a group of people in that field who basically look over your data, look at all your sources. Where'd you get your initial data when you collected your research? Look at how you formulated your hypothesis. Look at the numbers. Look at how you conducted your test. And if there's something wrong with it, they'll send it back. If it seems all right on the surface, they'll allow it to be published. But even that point, once you're published, that's only the first part of the process. You can have dozens of papers and articles on one particular subject and one particular set of experiments. Especially if you find something that's a little bit unusual in the data. People go back and try to recreate these experiments over and over again. They'll have their own hypotheses and their own lab experiments. They'll go back and forth. Because you have to understand, scientists are actually very competitive, like finding things out. They especially being the first one to find something. Especially if they can prove a colleague wrong. That's what the communicating results is. It's scholars talking each other back and forth until generally there's consensus and they move on. But even then, once the consensus is reached, that yes, this initial hypothesis was correct, this data initially was correct, they're still doing research on it. So this is the general method they've used in science since about the 18th century. Since Sir Francis Bacon basically modernized this system. And it's been used in science classes ever since then. Now, fields like history and political science, literature, and so forth, they don't necessarily have to go through this entire process the same way because sometimes there's nothing really you can experiment with. Actually, what are you going to test in history? You're going to go back, build a time machine, and conduct a series of experiments back and forth? You just can't do that. But the principle's still the same in all these fields. Do your research. Always do your research. Look at what the research means. Draw your conclusions. Communicate your results. Tell the world. Sometimes it might be onto something groundbreaking. Sometimes you're not. Sometimes you found something that's just interesting. People haven't really talked about much. But again, it's the same principle. But overall, the most important principle here in the scientific process is pursuit of truth. For facts, look for what's correct. Integrity matters in all fields of research in academic matters. Which gets you to things like logic, reason, fact, and of course, critical thinking. In science, in geography, trust the numbers. Look what the numbers say. Look at what they're telling you. What direction they're taking you. And that's what we're doing with this. Look at the numbers. Look at the data. In this case, we're looking at the Earth from all different angles. From the atmosphere down in, from the ground up, everything all around the world, different people, how they're using it, different regions, they react, and so forth. So we get to the question here. What is critical thinking? Hand out here. So it's basically the principle here, critical thinking. Get a close screenshot of that. So, critical thinking, it's an element in logic, and it's emphasized a lot in all academic pursuits. What is first is it's independent thinking, or thinking for yourself. Now, thinking for yourself, it's not having an opinion that's different from everyone else. It's not coming up with some kind of oddball. That doesn't make you an independent thinker. For example, people who say the Earth is flat, that does not make you an independent thinker. Being wrong doesn't make you an independent thinker. It just makes you wrong. You take all the data, all the scientific principles, and just ignore them. That's not thinking. So, yes, the Earth is flat. Why? Because we've observed it as a round sphere. So, not flat. No one's taken that idea seriously for at least people with proper mental health have not taken the idea of a flat Earth seriously in centuries. If they ever really did. Round Earth. You just have to understand the way we think and what we think is influenced by a lot of outside influences. Influences we may not even be aware of fully there. It's like a psychologist friend of mine once said, suppose a fish were a scientist. You have a scientist fish. What would be the last thing he discovered? Water. Because he's surrounded by it all the time. Doesn't think about it. So critical thinking is important because many of our beliefs are acquired at an early age when we have a strong tendency to form beliefs for rational reasons. Just because we want to believe, because we're praised or rewarded for believing. Sometimes people look for data that conforms to their beliefs. They call that confirmation bias. They say that's not going where the facts are taking it. That's not looking at the data. That's taking the data where you want it to go. It's the tail wagging the dog, so to speak. So critical thinkers, what do? They know how to raise questions. Remember, the purpose of question, it is to find out answers. It's not to disprove something. It's not to criticize something. It's to learn more, to get more data, and to go to where the facts will take you. Critical thinkers know how to use critical thinking skills and insights to reveal and reject beliefs that are irrational, things that are against reason, that are against the facts. Sometimes you want something to be true so badly, you can taste it, even knowing it's wrong. Like watching the Dallas Cowboys getting blown out in that game. So many fans wanted to believe, oh, they still got a chance, but no, they didn't. The facts just weren't there. But critical thinking, it is learning to think outside the box, learning to look at a problem from a different angle. Remember, critical thinking, logic, and reason, they're not there to destroy your belief system. They aren't there to completely overthrow everything, every thought and idea you hold dear. It's there to show you what the world really is. What you do with that information, that's up to you. It's not there to overthrow everything you see about the world. So yes, look at things from a different angle. Look at things from a traditional angle. But be willing to look at the facts. To put your own wants and feelings aside, just to look at what do the facts say. So do not passively accept beliefs of others in forming new thoughts and try to figure out things for themselves. That's what critical thinkers do. So yes, in a sense, being a little bit skeptical is okay, but not a total default mode. There comes a point where the questions are answered, and it's time to start a new series of questions to find out something else. Now, it's like ancient Greek philosophers would say, wisdom is being able to hold two separate ideas in your head at one time. Something you disagree with, an idea you agree with, an idea you disagree with, to hold those together and not necessarily uh, change your mind just because you're thinking about something different. It's okay to look at a contrary idea. It's okay to ask questions about things you believe, because that can often lead to a deeper appreciation and deeper insight for what you do believe. Critical thinkers know the difference between rhetoric and logic. So remember, what we're talking about here, logic, reason, fact, scientific method, science. Science is not a popularity contest. Something doesn't become an accepted fact because a majority of people happen to believe it. So we don't do science by Gallup poll. We do it by research and experimentation. Push through. We find out the facts. We see where those facts from that data takes us. Critical thinkers are not limited by the accepted ways of doing things. It is you're willing to try something different. Not discard old ways, but consider new ones. Critical thinkers don't accept as true or reject as false beliefs they don't understand. That is, just because you don't like it, just because you don't understand it, doesn't mean that's not the way it is. You have to be willing to clear away your misconceptions, clear away your own wants, and just, again, look at the data. It's like what Joe Friday used to say on that old cop show, Dragnet, real popular years ago. Somebody they'd be interviewing somebody who witnessed to a crime. Somebody's really upset, and they'd be saying what they think about this, that, some other thing, going off on a tangent. And Joe Friday'd say, "Just the facts, ma'am. Just Just the facts. And that's science. Just the facts. Just what matters. At least in the case of finding out the answers to these questions. And of course, one thing about critical thinking is realizing you're not perfect. Humility is an important part of learning. Now, there's a difference again between humility and to humiliate. Humility, you're humble. You're not obsessed with personal pride or ego. It's you understand, you realize they're experts in this field who know more than you do. Because no matter what field you're in, there's always somebody who knows something more, a little bit more about something that somebody else does. Like say you go to a doctor, sometimes they send you to a specialist. Does that mean your doctor doesn't understand the problem? No, it doesn't mean he doesn't understand. He understands it, he knows it, but he has the humility to realize there are people better equipped and better suited to deal with an issue than he may be as a general practitioner. He may know all the latest findings. She may know all the latest techniques. These doctors also know there are people whose jobs it is just to specialize and look at this problem. So, yeah, humility. Understand that, yes, there are people who know more, that there is always something more new or better to learn. And also understand that, yes, sometimes you make mistakes. Sometimes you can be wrong. That's what critical thinking is. So we'll dive in a little more here. Look at the idea of logical fallacies. So, logical fallacies. That one right there. All right. Logical fallacies are common errors in reasoning that will undermine the logic of your argument. Like I said, just the facts, but it's easy to take facts and apply them in the wrong direction. It's easy to make mistakes with it. Because again, we're human beings. We make mistakes. We get carried away with our feelings sometimes, and sometimes lose sight of our goals. So logic and reason, academics, it is a disciplinary process. As human beings, we're not perfect, though, but we have to be careful about these. To look for these in our own arguments we make, but also make sure you're aware of them in the arguments that others are making. Now, these fallacies can either be illegitimate arguments or irrelevant points, and are often identified because they lack evidence to support their claim. So make sure you avoid these common fallacies in your own arguments. Watch for them in the arguments of others. For example, the slippery slope. You may have heard that often. This is conclusion based on the premise that if A happens, then eventually, through a small series of steps, through B, C, D, E, F, all these, or X, Y, and Z, all these other things are going to happen too. Basically equating A and Z. That if this one thing happens, everything's going to happen. There's nothing to stop it. This whole domino effect of results from this one little thing. Well, it doesn't quite work like that. Give an example here. If we ban Hummers because they're bad for the environment, eventually the government will ban all cars, so we should not ban Hummers. In the slippery slope. You get rid of one kind of car means eventually you're going to get rid of all of them. Not necessarily true. what you have to do is look at each result on its own merits. So we're going back here to our testing hypothesis. What happens in our experiments? What happens with the data? Sometimes one thing may lead to one or two things. Sometimes there are several different things that do happen, but not always. So we have to look at each question on its own merits, each result on its own merits. Causality. It's a conclusion that assumes if something occurs after an event, then that event must be the cause. See, one thing does not necessarily cause another. Example, I drank a bottle of water and now I'm sick, so the water must have made me sick. This example, the author assumes that if one event chronologically follows another, the first event must cause the second. If the illness could have been caused by the burrito the night before, flu bug that had been working on the body for days, or a chemical spill across campus. There's no reason without more evidence to assume the water automatically caused the person to be sick. Look at the data. It doesn't have to be data doesn't have to be a bunch of numbers on a spreadsheet. It can be what you see, what's going on around you. This is because you see one thing happening doesn't mean the next thing is the cause of it. It's caused by it. There's a such thing as we like to call coincidence. Coincidence. A coincidence just means that it coincides with it. They're not necessarily related to each other. So I got to be careful about it. Again, go back to the facts. What was the cause of this thing happening? Not what happens afterward. Not chronology. Causality. See what happens because of it. Because two events happening in a similar time period, or one after another, they may just be coinciding with each other. Completely by accident and completely unrelated to it. Look at the data and see what is the cause. Begging the claim. This is the conclusion of the writer should prove is validated within the claim. Example here: filthy and polluting coal should be banned. Okay. Well, here has begging the claim. So arguing that coal pollutes the earth and thus should be banned would be logical. But the very conclusion that should be proved that coal causes enough pollution to warrant banning its use is already assumed in the claim by referring to it as filthy and polluting. This basically, you editorialized already. You want people automatically to think a thing just how you're presenting it. You're not presenting the facts, you're presenting your opinion and your conclusion at the same time. Filthy and polluting coal. Now, how you not beg the claim is, would say something like, studies have shown that coal causes a lot of pollution. Therefore, coal should be banned. Something along those lines. Again, just an example here. Again, let the facts do the talking. Circular argument. This restates the argument rather than actually proving it. Example, John Smith is a good communicator because he speaks effectively. That's a circular argument. You've declared him to be a good communicator because he speaks effectively. And why is he a good speak effectively? Because he's a good communicator. What happens with the circular argument is it becomes its own little world, its own little ecosystem. It doesn't allow anything else into it. No other facts, no other information. It just feeds on itself. It's an endless loop. So, conclusion that Smith is a good communicator and the evidence used to prove it is that he speaks effectively are basically the same idea. Specific evidence, such as using everyday language, breaking down complex problems, or illustrating his points with humorous stories, will be needed to prove either half of the sentence. Again, you got to allow room to allow in more facts and more data. Yeah, John Smith could be a good communicator. He could speak very effectively. but you aren't allowing any evidence into that one way or another. Your circular argument could actually prevent you from proving your point. The either or. This is a conclusion that oversimplifies the argument by reducing it to only two sides or choices. Example here, we can either stop using cars or destroy the earth. Pretty drastic. In this example, the two choices are presented as the only options. Yet the author ignores a range of choices in between, such as developing cleaner technology, car sharing systems for necessities, emergencies, or better community planning to discourage daily driving, or better mass transit systems. Basically, the either or argument, it's also called the all or nothing argument. Either we ban cars or we're going to destroy the world. Like say that, the next time you turn on your car, the next time you hit the ignition, the world's going to blow up. No, it's not all or nothing. These two things obviously are not related, so it's not logical to connect them like this. So don't go to extreme examples. And don't use the either or argument, or it's also known as the all or nothing. The bandwagon appeal. This is an appeal that presents what most people or a group of people think in order to persuade one to think the same way, or the everybody's doing it argument. Basically, all the cool kids are drinking Gatorade now. So therefore, if you want to be a cool kid, you got to drink Gatorade like all that they are. Or everybody's behind the Atlanta Braves this year. Everybody wants them to win. So you might as well get on board and support them too. Or everybody's wearing Nikes this year. That's again appeals it's an emotional appeal. It's people want to be included. People want to be part of the popular crowd. People want the approval of that crowd. So bandwagon appeal works that way. Example here, if you were a true American, you'd support the rights of people to choose whatever vehicle they want. This example, the author equates being a true American, a concept that people want to be associated with, particularly in a time of war, with allowing people to buy any vehicle they want, even though there is no inherent connection between the two. For example, I could be in France and want to everyone be able to drive whatever vehicle they want. Does that make me true American? No, because I'm not American. I'd be French in that case. Like I say, patriotism not being based on the idea of what car you drive. This is sometimes also called the true Scotsman argument, based from an old literary example that no true Scotsman would allow this to happen. Kind of the same way, bandwagon appeal. The red herring. This has nothing to do with fishing. The red herring is a diversionary tactic that avoids the key issues, often by opposing arguments rather than addressing them. This is the what about argument. Now, what about? People use this a lot when they're trying to deflect from a losing argument. They try to put up examples or try to change the question, try to change the narrative instead of focusing on what's the question at hand. What are you trying to figure out? An example here of the red herring argument. Yes, the senator stole millions of dollars. What about when the opponent lied about lowering taxes? Again, the what about argument. Yeah, you did this, but what about? What about? What about? I said, what about his opponent wasting billions of dollars of taxpayer dollars? Never mind the fact the senator did this. What about this? Again, ignoring the primary question. The senator stole millions of dollars. The senator broke the law. Question is about what anybody else did. The question is, what did this senator do? Again, the red herring. Don't be distracted by something else. Or somebody shouting, squirrel, and everyone looking aside. Yeah, so avoid the red herring argument. Avoid the what about. Concentrate on the question at hand. And don't let anybody try to steer you away from that. The straw man argument. This move oversimplifies an opponent's viewpoint and attacks that hollow argument. Example, people don't support the proposed state minimum wage increase, hate the poor. Basically, you're attacking the messenger. That is, you're not looking at the facts, you're looking at who's delivering the facts. Um, for example, go back to our senator stole millions of dollars argument. Um, some people might say, yes, the senator stole millions of dollars, but the guy accusing him is an alcoholic, trying to find some way to discredit who is delivering the information. The newscaster announces the senator has stolen millions of dollars, but someone points out, yeah, but the newscaster is cheating on his wife. That's the straw man argument, attacking the messenger, versus the red herring, just distracting it. So in this example here, people don't support his minimum wage increase, hate the poor. He's attributing the worst possible motive to an opponent's position. In reality, however, the opposition probably has more complex and sympathetic arguments to support their point. But by not addressing those arguments, the author is not treating the opposition with respect or refuting their position. Again, it's not what the data may not be what the data in this case is saying, why this person is opposing that minimum wage increase, just as an example. And finally, moral equivalence. This fallacy compares minor misdeeds with major atrocities, suggesting that both are equally immoral. It's also called the false equivalence argument. For example, here, that parking lot attendant who gave me a ticket is as bad as Hitler. It's also the common Facebook argument. Everyone I disagree with is Hitler. In this example, the author is comparing the relatively harmless actions of a person doing their job, simply enforcing the law and issuing a mild citation, with the horrific actions of Hitler, a man who killed millions of people. The two are not the same. The comparison is unfair and inaccurate. False equivalence, or moral equivalence argument. It's also the apples and oranges argument. This is trying to compare two things that are not related. So that's your logical fallacies, things you need to watch out for in science. And just look at the data, look at the facts. What we also got here, though, is the classic Bloom's taxonomy of logic, or how to find things out logically. Logic, Mr. Spock. So, Bloom's taxonomy. Okay. Now, logic isn't just necessarily something used as a conversation topic on Star Trek. It isn't necessarily something just used in computer science. It's something can be used in many different fields. Well, this process of the scientific method, it is relying on logic. What are the facts? And there's steps in logic, steps how you find things out. For example, an attorney. It's often been said, quite famously, that an attorney who defends himself as a fool for a client. There's a reason behind that. What does a lawyer do? Doesn't just represent you in court, doesn't just file things on your behalf, but he looks at the data, looks at all the information back and forth. And a lawyer, since it's somebody else, someone trained in law, an expert in law, but also someone who is a little bit detached from the situation, they don't have the same emotional immediacy. They're not carried away by it. They're not upset. You need someone calm, cool, and collected who can cut through all the extraneous things, all the emotional arguments, and just look at what are the facts. What actually happened here? What is the law? So this approach works in science also. What are the facts? Not what you want to be true, what is actually true. So, quite famously put together as Bloom's taxonomy. I've been learning about this since I was in elementary school, but it works. These steps in order, compiled by psychologist Benjamin Bloom in 1956, are basically how do you find things out logically? That is deductive reasoning. Deductive reasoning. And there are multiple steps. It's not just enough to be able to recite information. It's to be able to know how do you apply information? How do you process it? That's where we start here. Knowledge. Knowledge is the most basic step in logic. Facts, the data. What is it? Knowledge. Briefly stated, to define, to name, to memorize. That's the most basic and elementary form of it. You've got the information, you've got the facts. But you have to know next, what are you going to do with it? Do you understand what you have? The Treaty of Westphalia was signed in 1648. Okay, that's a fact. That's knowledge. But what does it mean? Do you understand what it is? Do you know how to apply it? Do you know what the context of it is? You know what the Treaty of Westphalia even is? It's a treaty that ended the 30 Years' War in 1648. Okay. Now understand this. Truth is the foundation of knowledge. Fact is the foundation of it. Knowledge comes from facts. Verifiable, demonstrable facts. And knowledge is the foundation of wisdom. Truth to knowledge to wisdom. And what knowledge is not, it is not lies, myths, half-truths, or prejudices. It is fact. So knowledge comes first. Comprehension is the next step. 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 Comprehension, briefly stated, to express, to describe, to explain, to interpret. With comprehension comes understanding, a step beyond memorization. You've got the facts, you got the data, but you don't know what it means. Next step, comprehension, understanding what it means. What comprehension is not. It is not thinking you know everything about a particular idea or subject from just a few brief glances at it. It is not asking a series of questions to avoid answers you don't like. Comprehension, it's able to express and describe it. Basically, you take it and you can rephrase it. Rephrase it in a way that does not eliminate any of the facts or any of the truth about the basic knowledge you had about something. It's showing that, yes, you do understand what it means. Not comprehension. Next, say when you are in elementary school and junior high and high school, they may have brought up the term reading comprehension. What it means is a step beyond simply being able to read something. You can read something on a piece of paper, but do you know what it means? That's the next step. Basic knowledge of reading. Basic knowledge that, yes, you can read this sentence and memorize it. But the next step, do you understand what you just read? Comprehension. Next step, analysis. Analysis. To compare, to differentiate, to question, to calculate. With analysis comes the step of looking at the different parts of an idea, see how it comes together and works, as well as how looking how it relates to other ideas. You can break it down into its separate pieces. You can see what makes it tick. It's like, okay, you've got a clock. You see it. You know, this is a clock. You understand what it does. It tells time. But then you take the next step, analysis. You look at how it works. Look at the LED functions. Look at the numbers on it. You understand it's plugged in. You notice they're electric. You can take it apart, look at the different parts that make it work. Analysis of it. Now, what analysis is not, it is not circular reasoning. It is not, going back to our circular arguments, it's not an airtight way of thinking that allows no room for other facts or new information. It's looking at the different parts of it. Looking at how it relates to other ideas. So you've got a digital clock, but you also notice, oh, there's an old mechanical clock, an old grandfather clock. Those are both clocks. They both do the same things. They both tell time. They're made differently, but they both do the same job. Analysis. And go back to knowledge, comprehension, analysis. Next step, application. You start getting into the higher levels of a logic. The higher levels, it's not just knowing what it is and how it works, but knowing what you can do with it, what you should do with it. Application, to illustrate, to use, to dramatize, to practice. With application, ideas are put into action. Again, going back to the clock argument. You have a clock. You know this is a clock. You know what it does. It tells time. You know how it works. So we start doing with it. You start applying with it. You start using it to time different things or to set schedules based around it. Application, okay, I have to be here at 6 o'clock, and I know it is 3:30 right now, means I have 2.5 hours before I have to do this one particular thing. Application. You're using the clock. Or it takes me 2 minutes to walk to the house across the street and back into the same room. Application. And ideas put into action. Remember what application is not. It's not using any random maxim or rule of thumb or slogan or way of thinking to any situation, no matter the facts. That is, you don't try to fit a square peg into a round hole. For example, social Darwinism, famous concept for the 19th century. It was never a logical idea. Why? Darwin's theory of evolution only dealt with biological processes based on the logical deduction from existing knowledge. It cannot logically be applied to human social interactions and moral questions because the two are completely separate ideas. Biological evolution and human morality, those are separate concepts. You cannot use one to justify or apply to the other because they just don't fit together. At least in terms of what to do about the poor or foreign policy questions. So, Darwin's theory of evolution cannot logically be applied to human social interactions. The two are not related, therefore, do not apply to each other. But other concepts can be applied in other ways. For example, okay, let's go back to Darwin's theory of evolution for a minute. How can we apply that? We can use it to see how microorganisms change over successive generations, to see how it can better develop a better vaccine or better antibiotic. We can, again, going back to the clock example, use it in different ways to time things, set schedules, all sorts of different ways to apply it that are logical and reasonable. Next step, synthesis. Synthesis. To compose, to formulate, to plan, to design, to construct, to create. Synthesis is not always a must with logic, but it becomes a possibility through the proper steps of understanding it. I know how to apply all these different things. I know what they are. But I can also figure out I can create something new from it. Going back to our clock example. I know different things can be used for. What does it mean now? I understand the parts, I understand what makes it go. I can also invent and develop a better clock on my own. With synthesis, ideas are combined into new ideas in the form of art, writing, abstract thought, and other creations. What it is not simply putting together random quotes or plagiarism. For example, go to your research papers. These research papers are not going to be put together by you copying from someone else. Copying from someone else, plagiarism, it's unethical on one hand, but also in terms of logic, it's not synthesis. You're collecting information and putting your name on it. Presenting someone else's work as your own. That's not synthesis. That's not creation. So, Danish philosopher Soren Kierkegaard had an interesting idea on synthesis. So how do we find out facts and how do we find out truth? Well, for Kierkegaard, the idea was thesis and antithesis. Have a thesis, have an argument, have a fact. And the antithesis, the opposite of it, or falsehood. Are actually two opposites in this case. Thesis and antithesis. Two opposites. You put them together. What cancels out? What's left over? And that process creates synthesis. You created something new, a new truth, a new fact, by examining two ideas, putting them together, and seeing what comes out. Again, the idea of Kierkegaard, though, is always starting with truth, starting with facts, using logic of this combination, mixing, matching of thesis synthesis to produce this new idea, this new synthesis. And from there, it starts over again. Last step in Bloom's taxonomy is that of evaluation. Now, a lot of people try to put that first for even knowledge, but no, this is the last step of the process. To estimate, to value, to praise, to predict. And going back here to the scientific method, from these collecting your data, from testing it over and over again, from drawing the conclusions. One of the conclusions you can draw is you can make predictions. What's going to happen in this experiment when you mix this and that together? What are you going to produce? Some new substance, an explosion, what? You can predict that from the conclusions from testing this hypothesis over and over again. Now, evaluation is the top point of the logic pyramid. It is using evidence to form a conclusion or set the stage for more research. Knowledge, learning, and reason, remember, these are never-ending processes. You're always going to be learning. Logic is a never-ending process. Knowledge is a never-ending process. Learning, it's all vital. It's all important. Because there's always going to be something new coming out. Remember what evaluation is not. It's not some knee-jerk reaction. It's not an opinion. Not a preconceived notion or emotional feeling toward an idea or fact. For example, hearing a news story and immediately saying, I disagree or I don't like it. That's not critical thinking. That's not deductive reasoning. That's just an emotional reaction. That's not evaluation. However, reading different sources and comparing facts and learning as much as we can available on a particular topic, that can lead to proper evaluation. Now we go back here to estimation and valuation. I look at this beautiful vase and just saying, I don't like the colors on it, I think it looks ugly, it's worthless. That's not valuation. That's an opinion. It's a knee-jerk impulse reaction. To value it, it's you look at it critically. Not to criticize it, but just look at its merits. Look at the different paint styles. Look at the age on it. Look where it comes from. If other people might want it. And that vase you're putting a valuation on, it could be a priceless Ming vase. This may not be something you like or you like the aesthetics on it, but it could be something that's very valuable to a lot of people. Even though you may not necessarily like how it looks or understand why it's important to someone. Valuation. And finally, our clock example here. You've made the new clock and you evaluate it. Our clock's good? Our clock's useful? Or you can predict. Creating, building more clocks, what's going to happen because of that? People may buy them. People may only want to buy certain kinds of clocks. Now remember, knowledge is always the foundation of logic and of deductive reasoning. And to understand, you must first know. Knowing is the first part. From there, you can analyze in order to fully evaluate at the end of the process. In other words, to think critically, you must know and understand and be able to analyze an idea and understand how it's applied. first knowing the most important thing, but then understand it, analyze it, look at its pieces, looking how it can be used. Give another famous example from history, the telephone. Invented in 1876 by Alexander Graham Bell. Okay, he had the knowledge. He was able to put together from this knowledge, able to put together a telephone. Knowledge. This is a telephone. This is what it does. It allows people to communicate across considerable differences through a telephone wire. Comprehend, you understand that. He analyzed it. What are the different pieces put together to make a telephone work? Telephone, the pieces that make it work, the telephone line, and the telephone at the other end of that line. Application, knowing how it can be used. Now, the telephone first came out, application was a problem because it's something that made sense, but no one knew how to. A lot of people didn't know how to apply it. For example, President Rutherford B. Hayes had a demonstration of the telephone by Alexander Graham Bell at the White House in 1877. Bell showing President Hayes, this is a telephone, this is how it works. Well, Hayes thought it was a really neat little device, but he didn't know who would ever use one. Who's going to use a telephone? Why? Because they had so many other ways of communicating at that point, they didn't think about a new way to communicate. If I want to talk to someone, I want to send a message to someone, I'll write them a letter, or I'll go over and talk to them in person. I have a messenger, send a message over to them, and the messenger bring that back. If I really want to talk to someone really quickly, I'll send a telegram. The idea of voice communications, someone of a great distance, just didn't occur to them. Or why someone would want to do that. Mark Twain, he understood there would be value in it. He once famously said he could only think of 3 people who would ever use a telephone. His banker, his publisher, and his lawyer. The only people he'd know who would use it. And just didn't see the applications of it. But not being able to see the immediate applications, that's not as important. You still have to build on the basis of knowledge and comprehension and analysis. Sometimes application, you have to see how other things are coming into it. Why someone would want to use this, how it can be used. Then from synthesis, learn how to make a better telephone. So the first telephones, they weren't direct dial. You had to contact the operator, tell them who you wanted to talk to, and then they would connect you. A direct dial rotary telephone was the next step. Then from there, push button phones. Then somebody got the idea, well, why do we need wires to these phones anyway? We can just, why can't they work like a walkie-talkie? So, cell phones came along. Synthesis. Or with the cell phone, initially it was just simply to call people with. The earliest cordless phones, they didn't have text functions. Basically, it's basically a remote control telephone. That's it. And say for a kid like me, growing up in the 1980s, the idea you could take pictures with a telephone just something just didn't make sense. It'd be like saying, yeah, so one day I'll be able to take pictures with our phone. Okay, this phone that's connected to the wall, the record. I'm going to take pictures of that. That made about as much sense as watching TV on a refrigerator. But you can actually do that now too. The newest models at Home Depot. But they started adding more functions to it as they sort of realized how the electronics work and how they can combine. I can use this to send text messages, and they realized I can use send emails too. I can use it to, I'm using it to send emails. I can always use this as a camera too, and send those pictures by email, by text, and all sorts of other functions. Play games on it. And before long, the portable cell phone is able to do all sorts of things. Synthesis. Then evaluation. Value it. Appraise it. predict what's the next step of the process for the fund. That's all logic. That's all what science is. Knowledge, learning, research, understanding, applying it, and then looking for the next great thing to come along. But always, truth comes first. Truth is the basis of it. Just the facts, ma'am. Okay, any questions on anything? No? Okay, remember chapters 1 and 2 for next time. We'll dive in a little bit more. See y'all later on.